Thanks for introduction and thanks for being here this morning. So I'm Jing Han. I'm from Ohio State University. So today it's a great pleasure for me to present our paper. Basically, we're telling you about how to efficiently train long context cases in your large language models. And it's not limited to just training. We can do like fine tuning or even like the pre-filling during the inference. So this is a work done when I was interning at Microsoft DeepSpeed team last year. So let's get started. So yeah, I always want to dive in with this very nice table. So this is what I grabbed from the Llama 3.1 technical report. So here are some backgrounds. So Llama 3.1 model is trained on this 128K context length, but it uses an incremental scheme. So when you go from like the 8K sequence length to 128K, you will see that you will need some GPUs in your context parallelism group, right? So if it's only 8K, then everything's fine. But it's 128K, then you need like 16 GPUs to do the context parallel. Again, this is just some background that I will dive in later. Out there, we have two like very famous context parallelism strategies. The first is ring attention. The other is DeepSpeed Ulysses. So this figure basically shows you that on a 1.2 billion GPT model, which is like very, very small model, and if you only use like Ulysses and you want to train like 1 million context lengths, then you will have to have at least 64 GPUs. Otherwise, you won't be able to train these models at all. And this is just, like I said, like a 1.2 billion model, which is very small. So why training long context is so hard? I guess everyone here is very familiar with these four components during the model training. So we have model parameters, optimizer states, gradients, and activations. So these four parts, they accommodate our GPU memory during the training. So the first three components, they are only related to how large your model is. For example, like number of layers, hidden dimensions, etc. So once the model is fixed, like this part of memory consumption can be perfectly estimated and it won't change. But for the activations, so if you look at the shape of your tensor, basically, the second dimension is here. I'm showing S, which is the sequence length. So as you increase the sequence length, you will see that your activations start to accommodate more and more memories until you face an out-of-memory issue in GPU. This is the results from the PyTorch memory profiler. So what I'm showing here is the actual training memory footprint of a 40-layer, basically a 30B GPT models. This is already with context parallel. So the left part is the forward pass, basically because this is the first iteration and we're using Atom, so the forward is like less memory consumption. And the right side is the backward pass. So anyway, so you can see there are some fixed blocks down there. So those are the model parameters like optimizer states. They're all fixed. But besides of that, you will see a lot of spikes on the top. Although each spike only exists for a small amount of time, but you can see the spikes are so high that sometimes it can even surpass the memory consumption of the lower part. And this is why you will see a lot of out-of-memory issues when you train your model on long context. So we take a closer look into like each operation. Where do those spikes come from? Here we'll only look at one transformer block or one layer. So for QKV projection, I take this as an example. You go from hidden state to correct hidden value. So this is 3 times of GPU memory consumption. And we identify that during the training, the bottleneck actually comes from the backward process of the attention. So even regardless of which attention you're using, flash attention or anything, you will have 8 times of GPU memory consumptions when you do the backward of attention. So right there, you can see there is a correct key value attention output. So this is results from your forward pass. And during backward, you have the gradient input, and you need to store your result to the gradient of QKV. So that this is like 8 times of GPU memory consumption. And right, you can see like basically we list out all the memory spikes in every operations in a transformer block. But of course, we only need to care about the bottleneck, which is the attention. Yeah, so to this, our contributions are as follows. So first so again, by the way, the method is called fully pipeline distributed transformer, or we call it as FPDT, and this is based on the deep speed MLSys. And in this work, we have three designs. The first is GPU trunking. So this is proposed to basically reduce the memory spikes. And the second is basically we're trying to offload some sequence to the host memory from the HBM memory. So this further pushes the maximal, supported context length to million level. Like I'm talking about like 2 million, 4 million, etc. And also we have a double buffer. Like I think double buffer is like very familiar idea to all of you, but we use it here because of course we want to keep it at the MFU as high as possible. We don't want the GPUs, to be idled. So just one result shown here. There will be more in the following slides. But on for A100 8 gigabytes and roughly a 7 billion model, we support like 2 million sequence length training, which is 16 times longer than state of the art. And we also achieve like more than 55% of MFU. So I think it's a pretty good result. And as I said, it can be used, it can be applied to both like training and pre-filling stage of inference. So just mention this because in pre-filling, you don't have the backward, you only have the forward. But in forward, you will see there are still some bottlenecks. So if you can reduce the spikes there, then you can apply similar strategies to the pre-filling. So here is the background actually. So I'm not sure, I think maybe some of you know this deep speed MLSys kind of context parallel design. So just for the background, I will just quickly mention it. So before attention, in this parallel scheme, before attention, each GPU only hold a piece of the sequence, but all the attention heads. So when doing the attention, the GPU will gather the sequence, but scatter the heads. So we'll see that each GPU have the entire sequence, but maybe one or two head. And after we perform the attention, everything is, scattered back. So to the, this is why we have like two all-to-all operations here. So the first two designs, I just want to put them together. So this is trunking and offloading, sorry. So what we're showing here is the input of the transformer block. For example, the size is S by B by D. So S is the sequence length, and you have batch size, you have dimensions. But what we do here is we basically slice the input trunk into multiple trunks. So each trunk is of size S by N and B and D, etc. So by control, how large the N is, we can actually control the size of the trunk. So we can control how many tokens are on your HBM memory, right? So this, of course, this is showing the first trunk, Q1, K1, and V1. And because we're doing like autoregressive models, so Q1 only needs to attend to K1 and V1, not the trunks following it. So for Q1, after we use all-to-all to pass the trunks to the GPU that performs attention, we can get the output instantly. But we also need to cache the K1 and V1 to the host memory because the following Q trunks will also attend to K1 and V1. So this figure basically shows you for like some later parts of the sequence, for example, QM, like the M's trunk. So for QM, KM, and VM, because QM has to attend to all the previous trunks like KV trunks. So on GPU J, every time it's very similar to flash attention, if that makes you easier to understand this thing. So every time you only operate on a trunk of the sequence and we get a partial output, like a single SM or like block in flash attention. And we just iteratively go through all the trunks, and every time we just update our previous partial results. We just trace the statistics and update results. And until we go through all the trunks, then we get the final output. So this is thanks to great works like online softmax and flash attention. Cool. Offloading can be slow. I think we all agree on this. If you only do this compute, load, compute kind of schemes, then you will find your GPU is constantly waiting for the next trunks to be fetched from host memory. So that is why we need a double buffer design. But sometimes double buffer won't work. So for example, if for element-wise operations like FFN or the like a ReLU function, for example, because the compute is ON and the data loading is ON, so you will never perfectly overlap your data loading by computation. But in our case, for the attention, gladly that we have our own square complexity in attention, which means that if you look at the figure on the right side, if you increase your trunk size to a certain limit, you will find that the latency of prefetching the next trunk can be perfectly overlapped by the current trunk's attention computation. So below that point, you will see you cannot really hide the prefetching latency. But after that point, like the prefetching latency can be perfectly overlapped, but we also claim that you're just wasting too much HBM memory because you're putting too many tokens on your GPU, and as long as your GPU is busy computing, you don't really need to put so many tokens there. You can just fetch next tokens while computing the current one. So therefore, you just need to pick the correct point. This is the point where everything can be overlapped, but also you're not wasting too much GPU memory. And this is the actual, like the profiling results. So this is on the PCIe Gen 4 system. And our results shows that, by the way, this is A100 GPUs. So we show that when our sequence is about like 64K, then the latency of prefetching the trunk is kind of like equal to the latency of the attention computation. That is why we choose the trunk size to be 64K. So this is profiling like a more detailed graphs here. So the blue line shows you the T-flops. So at 64K, we have a very relatively good T-flops. And the green line shows you the memory consumption. So you can go to like 128K, but you will consume too much memory and you don't really gain any more T-flops. So this is why we choose 64K as the trunk size. Okay, I have 3 minutes, I think. So this is the overall pipeline design. We don't use any kernel, we don't touch kernel in this work, so we use all like the PyTorch built-in functions and the hooks, for example. So these are 3 streams. Audio communication, computation, offloading, they're on different streams. And by just carefully examining the data dependency issues, we overlap most the host to device and device to host with the attention computation. But of course, this is like too complicated for the presentation here. So I'd like to skip this one, but jump to this table right here. So I just want to say big thanks to all the previous very great works out there, because like we have TensorFlow, we have activation checkpointing, we have offloading checkpointing, Ulysses, and the Zero family. So with some of the techniques plus our FPDT design, we are able to go to 4 million context size. This is on 8 GPUs, so like a very typical DGX node, and on 8 billion Llama 3 models. And we're able to maintain like a over 55% of MFU, which is much higher than the other solutions. Right. So I think this is probably going to be my last slides. But so this is like after we optimize everything, after we implement the trunking designs, this is the new memory profiling results. So you can see that by just adjust how many trunks you're going to use in attention as well as FFN, because these two are the bottlenecks, right? So you can actually control the peak memory consumptions during the training. So again, this is showing the backward. So you'll see the FFN comes first, then attention. So the trick here is that you want to balance both spikes. You don't really want to one part gets really high, because as long as you save more you save more memory on the activation layer, then you can increase your model size, which will be on the lower part of the figures. Right. And our code is available on DeepSpeed repo. So everything we pass the AE, for example, and you can just go and check it out. I think I'll stay here for a while.
Yeah, we have time for one quick question.
Yeah. Thank you. And also, thanks to all my co-authors and OSU and Microsoft. So I can take some questions.
Yeah, very amazing results. And I'm just curious, like you talk about different types, different shapes of different size of models, and you did the experiment in like specific GPUs. Like how flexible is this solution if, like in the future, there were different types or different GPUs.
Yes. That is a very good question. So actually, we found something very interesting during the rebuttal phase of our paper. So because in our paper we run everything on the A100 system with PCIe Gen 4. So in the rebuttal, one reviewer raises this question that can you test it on H100 systems? So we surprisingly found that if you look at all the vendors out there, so when you have this A100 system, they are often equipped with PCIe Gen 4. So for H100 system, it is often equipped with PCIe Gen 5. So the throughput of PCIe Gen 5 is almost like doubled that of PCIe Gen 4. But amazingly, if you measure the throughput of attention on H100, that is also about doubled compared to A100. So the conclusion is on H100 system, the trunk size is still 64K, everything is balanced there. But we do admit that in some cases where if you want to equip your A100 with PCIe Gen 5, then the things may be different because we want to change the trunk size to make sure the perfect overlap. If that answers your question. Thank you.
Yeah, let's thank our speaker again. And